Welcome to the video lecture series on contact mechanics in course M7033T, Scientific Computing with Applications in Tribology. My name is Andreas Amkes and I work at the Division of Machine Elements here at Luleå University of Technology. In this video, we're going to go through scaling and dimensionless formulations in general, and then the scaling the independent and dependent variables of the contact mechanics problem, and the dimensionless groups of this problem, and how to choose a suitable and, well, in some case even optimal set of scaling parameters. There will, however, be a cliffhanger in the end, but don't worry, it will be explained in more detail in part 7. A dimensionless formulation of a problem can be obtained if you scale your independent and dependent variables, and this needs to be done then by selecting some suitable reference parameters. For example, if t is an independent variable that represents time, then if we find tr to be a suitable reference parameter, we can formulate or describe the dimensionless representation of time as the ratio between time and the reference parameter. So let us consider the well-known relationship between distance and time here, which we see here S equal Vt, V times t, and V is then considered as an input parameter, the velocity, which is also assumed to be constant here. Then we scale the dependent variable s with a suitable reference parameter sr, and t we have already scaled, and we have the dimensionless t. This means that we can substitute these expressions into our problem, our model of how distance varies with time, and by this we can obtain, as you see here in the equation below, an expression for the dimensionless velocity, dimensionless distance in terms of what we have defined to be a dimensionless velocity and then dimensionless time. So we have this group V over S over SR over DR, and this is a dimensionless group of parameters, and this has been used now to define the dimensionless speed parameter V. And in terms of these dimensionless variables S, V and T, we have a complete non-dimensional model. In order to state the contact mechanics problem in dimensionless form, we have to consider both the complementarity problem itself and all the other governing equations. That one for the deformed gap, the deformation, and the force balance expression. And just to remind ourselves, we have 3 dependent variables. We have the deformed gap, H, we have the pressure, P, and the interference or rigid body separation, delta. We have independent variables, x1 and x2. We have input parameters in terms of E star. We have G, which is the gap between the undeformed surfaces, and we have W, which is the load that we apply on this system. Since the deformed gap is given by this expression, we have to scale GU and delta with the same reference parameter as H. And this means that we will have 4 reference parameters for this contact mechanics problem, and these are listed here. The dimensionless dependent and independent variables can now be obtained by scaling their correspondence with the reference parameters. So, since the expression for the deformed gap is this one, we realize we transform it to this expression where G, Ju, and delta bar are dimensionless representations of G, Ju, and delta, respectively. Let us continue to non-dimensionalized expression for the deformation. So in 3D, it reads, and by inserting the dimensionless variables into that expression, we get an expression for the deformation in terms of the dimensionless variables looking like this. The force balance equation also needs to be transformed into dimensionless form, and by doing so we obtain the following expression. This means that in terms of the dimensionless variables, which we see here, we can formulate the dimensionless contact mechanics problem as I'm not saying that this formulation of the contact mechanics problem is any simpler than the one-dimensional form. However, in the following, we will consider how to make this problem input parameter free, and then we will obtain something which is much simpler, and it is also much more generic. Okay, so the reason for the dimensionless contact mechanics problem looking more complex perhaps than the dimensional one is because of these parameter groups, which includes the reference parameters and input parameters. And we find two such groups in the expression for the dimensionless deformation, and one such group in the expression for force balance in dimensional form, non-dimensional form. And these are listed here below. You can see 1 and 2 are the groups that we find in the dimensionless deformation, and 3 is the group in the dimensionless force balance equation. In this case, we have 4 reference parameters, the ones for the different directions, x1 and x2, the one for the pressure, and the one for the deformed gap. We also have 3 dimensionless groups. 2 of them appears in the equation for the dimensionless deformation, 1 and 2, and the third one appeared in the equation for the dimensionless force balance. So we note that we are free to choose the reference parameters as we like, but with the restriction that the dimensions of them must match the variable we scale. Otherwise we don't obtain a dimensionless variable after scaling. In my mind, there are 2 main reasons for performing this scaling, and therefore there are 2 objectives of choosing the reference parameters. And one of them is to eliminate as many input parameters from the problem as possible, because if we do, we can solve the problem numerically for a very few variations in our input parameters, and then just scale back to obtain the results for a huge class of dimensional dependent variables. And then the other one, it may be to scale to avoid truncation errors. For example, the gap between the deformed surfaces is very small. So we may lose some digits on the mantissa during operations if we keep working with the original scale of the gap. And then here, by viewing these three groups and again contemplating over our problem, we really realize that we can eliminate one of these dimensionless groups without any loss of generality. Namely, we scale both the x1 and x2 coordinates with the same reference parameter. So by doing this, we have this updated dimensionless contact mechanics problem, and we can see that now we have only the two groups left, the 1 and 3, and what remains now is to try to make some educated choices of these reference parameters appearing in these, so that we can obtain an as input parameter free problem as possible. So it remains to choose the rest of the reference parameters, and we can choose the reference parameters for the length as the length of, or one of the major lengths of the contact zone that we consider. Let's denote this by L. Then we can define the reference parameter for the pressure as the total load over this length parameter squared, which obviously then is a pressure. We can choose the ratio between the reference parameter for the gap and this length parameter as the ratio between the load divided by the length parameter squared times pi times the reduced elastic modulus. And there is a beauty of choosing the reference parameters like this, which we soon will see, because in this case we will have a dimensionless force balance equation, which is completely free from input parameters, and we will also have a dimensionless deformation equation, completely free from input parameters. So our contact mechanics problem now may seem to be input parameter free, but we have a gap of the between the undeformed surfaces, G, and this one may contain more inputs. Let's see how this may be in different cases.